Welcome back. In the last few videos, we discussed some important theorems about fixed fields and defined Galois extensions, and I also gave you a few examples. So let me start today's video by recalling some of the facts that theorems and definitions I gave, and these are useful forms of useful results. Let me call it results to remember. So these are not written in words but written in just the notation of fixed fields that we learned. So there are three facts that we learned corresponding to two theorems and a proposition. So let K be any field. And the first fact, so I am not going to write the full details, and I only want to highlight as compactly as possible. Okay, so this is extension theorem 1. If you take any collection of homomorphisms from K to some field, the index or the degree of K over the fixed field is at least cardinality of S. On the other hand, if you take a group of automorphisms, you get a precise inequality. This is extension theorem 2. Remember, as I said, I am not writing the full hypothesis here. G is a group of automorphisms of K in this example. And using these, we proved also a proposition which says that the Galois group of, you take a field K, you take a group of automorphisms G, and the Galois group of finite group of automorphisms, Galois group of K over Kg is exactly G. These are always true. So this I called a proposition that I proved last time. So these are always true. Okay. So there is no other assumption on this. And the fourth is the definition of Galois extension. And I want to rewrite this as follows. A finite extension, whenever I write a finite extension, I mean a finite extension of fields always in this course, is Galois if the way to remember this is F is the fixed field of the Galois group of the extension. Okay, so this is a useful, this is the condition which makes this Galois. So in general, we have the fixed field sandwiched between K and F. The extension is Galois if the bottom part is exactly equal. Okay, so these are the useful things to remember from the last 2-3 classes. Okay, so today I am going to give you a few other ways to check if something is a Galois extension, and also I am going to introduce an important class of extensions called normal extensions, okay, which are like Galois but not quite. They are just slightly weaker than Galois extensions. Okay, so let me start with this theorem, which is a simple theorem given what we have already proved. Okay, so the statement is as follows: a finite extension K over F is Galois if and only if the cardinality or the order of the Galois group is equal to the degree of the field extension. So if you look back at the examples that we did, in all Galois extensions this happened to be the case, and in non-Galois extensions that fails. Okay, and anyway we will also see this again later when we do some problems. Okay, so it's a very simple proof as I told you. So in this direction, suppose so let K over F be Galois. So I am going to assume that this is a Galois extension. Then what we have is, it is right in front of you. By definition, F is the fixed field of the Galois group of K over F. Right. So by theorem 2 of extension fields of fixed fields, which I have written here, K colon Kg is, so in particular K colon Galois, K colon K power Galois, so this is equal to K colon F by the Galoisness, because F is the fixed field, so this is equal. By theorem 2, this implies this is equal to the cardinality of the group in question, right? So this is theorem 2. So whatever group comes here is the group that comes here. So that's all, right? So these are equal. So that's done. For the other direction, so if you have a Galois extension, then the order of the Galois group is equal to the degree of the field extension. On the other hand, assume that the order of the Galois group is equal to the degree of the field extension. And let L be the fixed field of the Galois group. Our goal is to prove that L equals F. We want to prove, but a priori it is a subfield of, it's an intermediate field. So a field that's sandwiched between K and F is called an intermediate field of this extension. So L is the fixed field of the Galois group. And now let's just check some things. So we know K colon L is equal to Galois, the order of the Galois group. This is precisely the statement that you have in theorem 2, right? So theorem 2 says that the degree over the fixed field is the cardinality of the group. But this is equal to K colon F by the hypothesis, right? So this is the hypothesis. But this is at least as much as K colon L, because L is an intermediate field. So this times this is equal to this whole thing. So K colon F is at least as much as K colon L. So we have K colon L on the left hand side, K colon L on the right hand side. So this implies that K equals, sorry, this L equals F. That is only possibility, right? Because K colon F is K colon L dot L colon F, but K colon F is equal to K colon L. So L colon F is 1. So L is equal to F. That means F is the fixed field, because L is the fixed field, but F is equal to L. So L is the fixed field. This is a nice test to check Galois, whether an extension is Galois, because this is a numerical test. In the definition, you have to look at the fixed field, and there could be some more work that you need to do there. But this is just a numerical check for Galois extensions. All you need to know is the Galois group, right? Otherwise, you can't check this. So if you know the Galois group and the degree of the extension, you know immediately whether the extension is Galois or not. We are going to make use of this later. Okay, so let me now prove another theorem, which is not really about Galois extensions, but it is about field extensions, and we will connect this to Galois extensions later. So let K over F be a finite extension. Always everything that we are dealing with is a field. K and F are fields, and K over F is a finite extension of fields. So I am going to fix an algebraic closure of F that contains K. So in fact, I can just take an algebraic closure of K. So from what we recalled about algebraic closures, you know that if you have an algebraic extension K over F, algebraic closure of K and F are isomorphic. So I can just take any algebraic closure that contains K. So then the following are equivalent. So this is a fairly simple proof. Nevertheless, it is an extremely important result in our course. As we proceed further, you will see that this is going to be very critical to us. If sigma from, so the first statement is, I am going to write 3 statements. The theorem asserts that they are all equivalent, so each implies the other. So if sigma from K to F bar is an F homomorphism of fields, remember K contains F, F bar contains F. So if K to F bar is an F homomorphism, if it's a field homomorphism that fixes every element in F. So suppose it is an F homomorphism of fields, then sigma K is contained in K. So that is the first assertion. So hence this in particular means that sigma from K to sigma induces an F automorphism from K to K. Remember that you have always an injective map from K to F bar. It's in fact inclusion, right? And you then have, by this condition, image of k is contained in k. That means sigma is a function from k to k. It's always injective of course, but it is also surjective by an exercise we did in the past. Okay, so if k over f is algebraic and sigma from k to k is an f homomorphism, then sigma is surjective. That is sigma k equals k. Okay, so this is an exercise that we did earlier. Okay, in one of the problem sessions I proved this, because the roots of k are finite, roots of a polynomial are finite, so those roots have to go to themselves. So you restrict to a injective map on a finite set to itself, and that has to be surjective. So every element of k is in the image. Okay, so once you have sigma k is contained in k, it induces an f automorphism. This is not quite required for the statement and the proof, but it's an important observation. So I wanted to record it in the statement of the theorem itself. Okay, second statement is, if f is an irreducible polynomial over the base field, is an irreducible polynomial which has a root in k, then it has all the roots in k. So then f splits completely. Remember our notation or meaning of the word phrase splits completely. That means that it splits as a product of linear polynomials in kx. That means all the roots of f in some large algebraic closure, or f bar in this case, actually lie in k. That is the content of the second statement. And the final statement is, k is a splitting field or the splitting field of a polynomial f in fx. So the extension k over f in fact is the splitting field of something. Okay, so this is something we are familiar with. Okay, this third statement actually is equivalent to 1 and 2 also. Okay, so the proof is not difficult at all. It's straightforward with all the theory that we have already developed. So let's just go through each implication. 1 implies 2. What is the statement? So this is in fact the crucial implication. The others are more easy. So this also is easy, but it requires more work than the others. So let's prove 1 implies 2. So let f in fx be an irreducible polynomial and let alpha in k be a root of f in k. Note that by hypothesis in 2, f is an irreducible polynomial, which is important. It has a root in k, right? So that then it splits completely. It can happen that, I am not saying that every polynomial splits completely. That of course will not happen. Only if it has at least one root, it will split completely. So let's take that one root that we are guaranteed. We know that f splits completely in f bar x, of course, because f bar is algebraically closed. So every polynomial splits completely. So let beta be any root. So let beta be any root of f in L bar. Then we have a sequence of isomorphisms this way. So we first have f contained in f alpha, which is of course in k, but f alpha is isomorphic to fx mod small fx. See, this is the point where we use irreducibility of f is crucial here. Okay, because only then this is a field. So this is isomorphic to that, but this is also same as f beta, because beta also has the same irreducible polynomial, but this is in f bar, right? So the upshot is we get f. So I'll try to write it here. So hence we have a homomorphism. So I'm going to write it like this. Right, so this is of course an F homomorphism. Right, because that is at every stage in this sequence, F is fixed pointwise. Every element of F goes to itself under all these maps. Okay, so this is the picture that we have. And of course, the point is this function, which is what I am denoting here, in fact this function sends alpha to beta, right. So because x, I can arrange it in such a way that alpha goes to x bar here goes to beta, so alpha goes to beta c. So under this map, alpha goes to beta. Now by the case here, by extension theorem that we proved, there is an extension like this. Let's call that sigma. So sigma exists, an extension like an extension exists by the extension theorems we proved. If you go back and look at those extension theorems, this is exactly the picture that we had. Any map like this can be extended because this is a finite extension, right? Okay, so algebraic extension was what we used. So this is certainly possible because it's a finite extension. Now apply 1. The condition 1. Sigma is a function from k to f bar, right? It is an f homomorphism. So sigma k is equal to k. Hence, beta, which is sigma alpha, is in k, right? So remember, alpha is in k, correct? So alpha is in k. Its image is beta, but sigma k is contained in k. So sigma of anything in k is in k. So beta is in k. So every root of f is in k. Okay. Hence, f splits completely over k. Or in kx, right? So this proves 2. Right, so if you have this property that any homomorphism from k to f bar has the property that its image is in k, then if you have a polynomial below, irreducible polynomial below, which has a root in capital K, then it must have all the roots in capital K, meaning it splits completely in capital K. Okay, so let me just give you a note here. It is important that f is irreducible here. So as you can see in this example, let's take q adjoint root 2 over q. So it's an easy exercise to show that it has this has the 3, we haven't proved equivalence, but we will prove it, the 3 equivalent conditions of the theorem. The best way to see that is, it is a splitting field, right? It has the third condition. It is a splitting field of x square minus 2, but it doesn't, I mean, it also has hence the other true properties, as we will show at the end of this proof. So take f to be, let's say x square minus 2 times x square plus 1. Okay, so I can take this x square. This has a root in k. K is this, f is this, right? Because it has a root, but it doesn't split completely over k, right? Because of course x square plus 1 doesn't have roots in k, because roots of x square plus 1 are non-real, but k is a real field. Okay, so that's obviously not going to split completely. So here f is not irreducible. Okay, so there could be factors which contribute roots, but you can't say anything about the other factors. So you can go back and see the proof will fail, because if you go modulo f, you won't get a field, or at least you can't say that it is isomorphic to the field generated by the other roots of this. Okay, so it's important. So I have taken a digression to prove that f being irreducible is an important condition here. Now let's complete the proof. Let's go to this 2 implies 3 statement, and these are now going to be easy for us. So let's take, so what is 2? 2 says that if an irreducible polynomial has one root in capital K, it has all the roots in capital K, and we are now going to show that it is the splitting field of a polynomial. So because it's a finite extension, we can write it like this. Let K be this, where alpha 1 through alpha n are in K, and suppose that, so we are going to assume that, suppose that we can't remove any alpha I. So by which I mean this is slightly sloppily written, but what I mean is that if you remove any of the alpha i's, it is not equal to K. So that means f of, for example, alpha 2, alpha 3, alpha n is not equal to K. So you need all the alpha i's to generate K. You will see, this is just a simple requirement, but you don't, if some alpha I is not needed, you just drop it. Okay, so this is nothing serious. Now let fi be the irreducible polynomial of alpha I over f. Right? So alpha i's are in K. They are of course algebraic, because K over f is a finite extension. So let us take the irreducible polynomial. Fi is irreducible and it has a root in K, obviously, because it has a root, namely alpha I. So and each Fi is irreducible, right? So this is the situation. So now apply 2. The statement 2 says that if an irreducible polynomial has one root, it splits completely. So by 2, Fi splits completely over capital F, or capital K rather. So now let us take the product of these as our F. Okay, so then F splits completely in Kx, right? Because the roots of F are the roots of Fi's, union of the roots of Fi's. Each Fi splits completely, so F itself does. And note that K over K is the field generated by F, right? Because you have to take all of K to generate the roots of F by this little hypothesis that I made. Even if you drop one of the alpha i's, you cannot get all of K. So so in other words, K is the smallest field, smallest subfield of K containing all the roots of F, because if it doesn't contain even one root, then you will get a strictly smaller field. Okay, so because alpha i's are all needed. Okay, so this shows that K is the splitting field. So this last point is trivial. If you don't need some roots, you can always drop it. The point is there is a single polynomial whose roots generate K. Okay, so now that implies 3. So finally 3 implies 1. If you prove this, you are done. You have proved 1 implies 2 here. You just proved 2 implies 3. Now we are going to prove 3 implies 1. So this is easy. So let K by hypothesis in 3 the splitting field of a polynomial f in Fx over capital F. So let us take the splitting field of a polynomial f in capital Fx over the field capital F. So suppose that roots are f are alpha 1 through alpha n. So k is equal to f alpha 1 through alpha n. Now let us take the hypothesis of 1. So let sigma from k to f bar be an f homomorphism. By our earlier results or remarks, sigma of alpha I must be alpha j, for every, okay, so this is, you understand what I mean here. So for every I, if you apply sigma alpha I must equal sigma of, it must be alpha j. So what I really mean is, I am not saying f is irreducible, so let me be a bit careful here. So by earlier results, for every alpha, sigma of alpha I is in this set. So because alpha I is irreducible polynomial, will be a factor of f, right? Because f satisfies alpha I. Alpha I is a root of f. So irreducible polynomial of alpha I is a factor of f. So its roots are also roots of f. But roots of f are this. So alpha I must go to one of these. But the way you might group this, you cannot say that every alpha I must go to every alpha j. That is incorrect. Because small f may not be irreducible. But you are guaranteed that root of the image of alpha I must map to one of these, alpha 1 through alpha n. But this is okay, right? Now we are done, because in other words, sigma alpha I is in k, right, for all I. So sigma alpha is in k for all I. This implies sigma of k is in k, right? So that's all. Because f is generated, k is generated by alpha I through alpha 1 through alpha n over f. Sigma f of course is f, because everything in capital F is itself under sigma. So all you need to worry about is alpha i's, where they go. But by this observation, image of alpha I must be again in k. That means any polynomial, every element of k is a polynomial in alpha i's with coefficients in capital F. So apply sigma to it and apply the field homomorphism property, you will again land in capital K. So this completes the proof of the proposition. The first statement is exactly that. If you have an f homomorphism from k to f bar, then image of k is contained in k, which is what we have just proved. So let me end this video with an important definition. A field extension k over f is called normal if it has a finite extension. It is a field extension, as I said, that goes without saying. A finite extension k over f is called normal if it satisfies any of the equivalent conditions of the above theorem. Okay. So the most familiar and probably convenient way of checking that is the third one, splitting field. So splitting field extensions are now called normal. So normal is a nice word for that, and it corresponds to the notion of normal subgroups of a group, as we will see later in the course. But a normal extension will also have these other two properties. See, if you just stare at this for a minute, it's important you can understand, because if you are taking a splitting field of a single polynomial, it has this nice property that every polynomial that has a root splits completely. So condition 2 seems on the face of it stronger than being splitting field of a single polynomial, but it is in fact equivalent to being the splitting field of a single polynomial. Okay, let me just add a final remark and then we'll end this video. Remark is that what is the connection of all these two Galois extensions? We will show later that a Galois extension is normal. This is true, we will prove this. This is an important observation, but the converse is not true. Meaning, there are converse is not true in general, let me say. there are normal extensions but which are not Galois. Okay. However, in characteristic 0, Galois is equivalent to normal for finite extensions, of course. Okay, so all this will be done later. So if you are working, for example, with extensions of Q, you can safely remove the word, replace the words Galois and interchange the words Galois and normal. So this is a new observation for us. Of course, this will be proved later. But once we prove that, Galois extensions are much more easy to understand in characteristic 0 because they are simply splitting fields of polynomials. But in general, and of course it has to be in characteristic prime, it is not true that normal implies Galois. It is only always true that Galois implies normal. So let me stop this video here. In the next video, we will do some problems to understand everything that we have done in the last few videos on Galois extensions. Thank you.